Ever wondered how first-order chemical reactions work? Well, sit back, relax, and prepare to unravel the mysteries of this fascinating world in the next 7 minutes. Imagine a chemical reaction as a busy kitchen, with chefs, ingredients, and processes all intermingling. In this culinary chaos, first-order reactions are the reliable chefs that always deliver a consistent dish, no matter how much they're in demand. They depend solely on the concentration of one reactant, much like a chef who only needs to focus on the quality of one key ingredient. In the realm of chemistry, first-order reactions follow a simple rule. The rate of the reaction is directly proportional to the concentration of one reactant. As a result, if you double the concentration of the reactant, the reaction rate also doubles. It's like adding more fuel to a fire. The more you add, the bigger the flame. An example of a first-order reaction is the radioactive decay of isotopes. Radioactive elements break down at a rate that is directly proportional to the number of radioactive atoms present. This means the decay rate will decrease over time as fewer and fewer radioactive atoms remain. Let's dive a bit deeper. The mathematical representation of first-order reactions is quite simple and elegant. The rate law equation for a first-order reaction is rate equals sign K, where rate is the reaction rate, K is the rate constant, and Y is the concentration of the reactant. The rate constant K is the chef's secret recipe, unique for each reaction and dependent on factors like temperature and pressure. A key characteristic of first-order reactions is the concept of half-life, which is the time it takes for half of the reactant to be consumed. In the case of radioactive decay, this is the time it takes for half of the radioactive atoms to decay. The half-life of a first-order reaction is independent of the initial concentration, meaning it remains constant throughout the reaction. It's like a chef's cooking time for a dish. It doesn't matter if the chef is cooking for 2 or 20, the cooking time remains the same. To sum up, first-order reactions are chemical reactions with a rate that is directly proportional to the concentration of one reactant. They are represented by a simple rate law equation and have a constant half-life. They are like reliable chefs in a kitchen, always delivering consistent results no matter the demand. So, the next time you're pondering over your chemistry homework or simply marveling at the world around you, remember these dependable first-order reactions. They're working tirelessly, following their rate law equations and ticking away their half-lives to make the universe a little more predictable. And remember, in the grand kitchen of chemistry, it's the first-order reactions that keep the culinary chaos in check.